Okay, so this is the astronomy video for topic 13. I'm going to look at 13.20 all the way through to 13.34. So 13.20, modern astronomical observations recorded using digital sensors. So I suppose if you are thinking about old-fashioned cameras, then you would have used film, and then we have our eyes that record light as well, and these are the photographic film captures an awful lot more light than our eyes do. But then you have an even more advanced thing that we use now, which would be a sensor, often CCDs, and these will be a lot more sensitive to light. So out of all the light that hits your eye, um, compared to the sensor will record an awful lot more of the light than the eye. So they're much more sensitive. They can record data as a digital information, and then they can process that and store it as files. So we have moved on. We've moved on from photographic film there. So that's the James Webb Telescope there, which is the modern telescope being sent up, and it's observing optical light. So that's visible light, which is right in the middle of the spectrum. 13.21 is understand how astronomers obtain and study the patterns of spectral lines. So if you take the light, white light, from a star, just like this would show, the white light can be split using a prism or something that would do the same job. And it would split into all the colours of the rainbow, all the different wavelengths. So if we do that with a star, what you'll see is there's these black lines, there's these gaps. So imagine this is just lots and lots of lines that need to line up together, but we've just chopped them and put them underneath each other. So it goes to the full colour of the rainbow. So these black lines are called absorption lines. And the absorption lines are specific to particular elements. So an astronomer will be able to tell you exactly what that line means and what that line means. So you'll be able to tell exactly which element absorbs that particular wavelength of light. You see, it's to do with something slightly beyond this course, but every element has particular levels or shells or energy levels where the electrons can exist. And when the electrons absorb some light energy, they can jump up an energy level, drop back down, and then they release that light. But the light gets released in a random direction, so a lot of it never reaches us. So these elements that are absorbing very, very specific wavelengths are kind of scattering the light away from us. It never reaches us, and it gets seen like a little dark patch in the spectrum. So we analyze this, and it gives us the chemical composition of a star. And actually, when we're looking at exoplanets, planets outside of our solar system, if they transit their star, so the star will go a little bit dimmer, some of that light will actually come through the atmosphere of the planet, and it will change this spectral pattern, and we'll be able to tell the atmosphere of the planet that's so far away. So that's clever. Okay, the next bunch you can read for yourself is based around this diagram here, which is really, really useful. It shows the full electromagnetic spectrum, and it gives an idea of how much of it gets blocked or how much of it gets through our atmosphere. So if we go through gamma rays up here, 100% of the gamma rays are blocked, which is very we're thankful for, really, because they'd be very harmful if they got through the Earth's atmosphere. And it's the same with X-rays as we go through, and then ultraviolet we get, and then we get a little drop off here. So some ultraviolet does get through our atmosphere, and then we get to visible light. And you can see the visible light, most of it gets through the atmosphere. Atmosphere does absorb some visible light, but it has a pretty good job of getting through. Then we go for infrared, which is a bit all over the place, and then you get into this over to the microwaves, and there's this window here, microwaves and radio waves, where it all gets through, and then the longer length radio waves do not get through. So really, if we want to observe the universe, which we do in all of the electromagnetic spectrum, then the atmosphere is not helping us a great deal. It's helping us survive, but it's not helping us observe the universe. So this radio window, as they call it, is observed an awful lot by us. We have our huge radio telescopes. They need to be very large because the wavelength of radio waves is very large. And then, yeah, visible light, optical telescopes, we have them and we use them on Earth. But because the atmosphere does block some of the visible light, then we would get better images if we go higher up mountains because it's got less atmosphere to go through, and also because it's sorry, and also we would send it out in space, which would mean that it's got no atmosphere to go through. If we want to study gamma rays, X-rays, then it has to be above the Earth's atmosphere because the Earth's atmosphere is blocking 100% of those. So yeah, we've got satellites in space that observe gamma rays, X-rays, ultraviolet, infrared, and each part of the electromagnetic spectrum is just as important as every other part. We need to study the universe in all parts of the electromagnetic spectrum, not just the visible light as you'd think. Okay, so as mentioned just then, radio telescopes observing the universe in that radio window there are incredibly useful to us. One of the problems with radio astronomy is that the radio waves are so large in wavelength that to get any detail from the information that we're capturing, we need a huge telescope. And then interferometry is the use of many radio telescopes acting as if they're one big dish, which helps us a lot to get the detail. So you're meant to understand the basics of how a radio telescope works. So you've got the dish, which will focus all the rays onto the antenna, and then that will get sent down to an amplifier, and then the signals can be processed. So it's pretty simple. Um, and then this idea of resolution. So they want you to understand that the reason behind the huge size of these, and some much bigger. Some have been built into valleys, and so here's an idea of resolution. So this is, you can clearly see that Hubble has a much greater resolution than Spitzer telescope here, because because the wavelength is smaller for Hubble, and we are getting a larger dish. So there's two factors that affect this really. So it's mentioned it here. So if you were to double the size of the thing that's um, capturing the rays, then it will be twice as good resolution. So if you double the diameter, then your resolution is twice as good. But if you're looking at something that has twice the wavelength, then the resolution is only half as good. So radio waves are way bigger wavelengths than optical. So we need to balance that. So the resolution will be awful. So we need to balance that out by having the dish really big. Okay. Next is this little one. Try to appreciate the importance of radio astronomy. One of the big stories of radio astronomy is the discovery of quasars. So it was this signal that we discovered emitting huge amounts of energy, and the spectrum, which is that colourful thing that we looked at earlier on, was showing elements that we didn't recognise at first, which was unbelievable. And we thought, well, how can something be showing elements that we've never seen before? And it turned out we later on recognised that they were just the elements that we know, but they were redshifted by huge amounts, which meant that they were really far away. But it was quite a strong source. So, how could it be that bright and yet be that far away? We assumed that it was close because it was such a strong source. So it turned out that these things called quasars are on the edges of our universe, and they are supermassive black holes at the center of galaxies, emitting huge amounts of energy that were first discovered in the radio range. So yeah, it's took us on really because, as I say, before 1940, as you can see there, it was all about visible light. So opening astronomy to all these other parts of the spectrum, we've learnt a huge amount more. Other things here, so you can see the array in Chile here. It's a beautiful scene, which is working, these are working together to collect huge amounts of information, and the resolution is made an awful lot better with these acting as one dish. Something else that gets mentioned is protoplanetary disks, which is the gas rotating around a young star, and radio waves helps us to record the data for those because the visible light doesn't get through. A lot of the dust blocks the visible light, so we needed to study it in another wavelength. Okay, so infrared astronomy gets a mention as well. So just an appreciation of infrared. Infrared rays are heat rays. So one thing that they discovered is what they call a hotspot on the moon here, which is down to volcanic activity, but not visible under visible light. But when you look at the subtle differences in temperature of the moon, then it's visible. Another thing as well is protostars. So a young star, before the star goes main sequence, which is when nuclear fusion starts, it's a protostar. And they were discovered using radio waves, and then molecular clouds as well. So these are huge clouds of dust and gas where stars will be formed. And again, if we view through the optical range, the visible light spectrum, then the dust and the gas is blocking the visible light a lot of the time. So we get an awful lot more information from from infrared. Sorry. Okay, so next we've got 13.34, and you can see there's quite a list here. It just says understand how a telescope alters the appearance of these. So you can see the website below where I took this really nice little table that explains it there. So we've got stars, is obvious what they are. Binary stars is where two stars are together, orbiting together. Double stars, you can have optical doubles which appear together, but they're not actually together. It's just because of the line of sight that we're looking at. You've got clusters. So globular clusters and open clusters, these are groups of stars. And then nebulae is where stars will be being born or maybe after the death of a star. And then you've got galaxies as well, which you should know what that is. So it just gives you an idea of how we can improve it. With obviously the telescope will give us better resolution. So if you look at something and it looks like just one dot, if you magnify that, get a better resolution, then you'll see it's actually two stars. So this just gives you a simple explanation of the advantages. Okay, and then this, why would we send things up into space? So there's pros and cons. I've mentioned already why we need to be above the atmosphere, particularly for certain wavelengths. So, a radio telescope wouldn't be able to be sent up because of the sheer size that it needs to be. But you've got gamma ray telescopes, infrared, X-ray, visible light, and they can take an image that it can stay and it can expose that image for days. And on Earth, of course, you can't do that because you can't be observing in the day, in the daylight. But Hubble has observed things for days, and the detail, letting in all that extra light, so you can get much more detailed images. So it's out the way of the atmosphere, obviously, and the atmosphere, you also have pollution in the atmosphere, which, not every place at sea level has the same sky quality. So you do away with that as well. But of course, it's expensive to build, expensive to send them up into space in the first place, and any maintenance costs a fortune on them. I think there's been 2 rounds of maintenance on the Hubble telescope in its entire lifetime, costs a fortune, and there's no more planned. Okay, and then it mentions the parts of the spectrum that we haven't really mentioned too much so far as well: gamma rays, X-rays, and UV astronomy. So UV, we can see, is tends to be linked with very old or very young objects. So we the interstellar medium in between stars, that's what it's talking about, is nicely viewed in UV, and you can see the sun in UV there. Now, X-rays are emitted by very hot objects and very fast moving objects. So actually the solar corona gives off a lot of X-rays, which is, a couple of million degrees C, and it's further away from the center of the sun than the surface of the sun, which is only about 6,000 degrees C. So, but black holes, when if they get close to a star, they can rip it apart, as you can see in this artist's impression here, and that will accelerate the particles to huge speeds. So then they will be given off huge amounts of X-rays. So they can be studied there. And gamma ray bursts get a mention. So gamma ray bursts occur at the death of a giant star in its supernova. And these are quite focused, and if it happened close to Earth, it would be a dangerous thing. And that they don't exist for very long, but they can be studied with gamma rays, obviously. So there we go. We are interested in every part of the electromagnetic spectrum. Right. Hope that was useful. Thank you very much.